Topic 4.5 deals with a special type of bonding, and we call it metallic bonding. And really what it is are the forces that are going to hold metals towards one another. We know that we see rings all the time, either tungsten rings, or we see silver or gold rings or other jewelry. What are the forces that hold those things together? So some of the key components of metallic bonds: they have a lattice of metal atoms, which we know have a low electronegativity value, and they have delocalized valence electrons. So their outer electrons are able to move around between all of the metal atoms, which then become more like metal cations, with those electrons floating around. And this is possible due to that low electronegativity value. They're not holding on to the electrons very tightly, and therefore they're able to move around more. The metal atoms can be thought of as cations due to delocalized valence electrons. And just in case you forgot, a lattice just means a structure that's very organized and rigid, and we know where those atoms are going to be, kind of like an ionic substance is. So here's two images that kind of represent what we have. We see here that lattice, that nice organized configuration of them in 3 dimensions. And this is a better idea of seeing those delocalized electrons, or sometimes it's called a sea of electrons because they're moving around. C is an SEA, and they're moving around those cations. But these cations, so the nucleus plus the inner valence electrons, are going to be basically stuck where they are until we start doing things like bending or shaping them, because metals are so malleable and ductile. So we've got a 3D lattice of metals there. Here's my delocalized electrons that are free to move. Metallic bonds have electrostatic attraction between the lattice. So we've seen electrostatic attraction with each of our types of bonds now. In ionic bonds, we had electrostatic attractions between anions and cations. In covalent bonds, we had an electrostatic attraction between the cations and the shared electrons. This time, my electrostatic attraction is between the lattice of cations, so that 3D structure of cations, and those delocalized or sea of electrons holding them all together. The cations are not bonded to one another. The only thing holding them together are those electrons that are free to move. These bonds are stronger when there are more electrons that are being shared and when the metals have smaller radii. So you can think of valence electrons, for instance, lithium compared to boron. Look at the periodic table right now. Lithium has 1 valence electron. So in my lattice of cations, each of them is sharing 1 valence electron. So that's going to be held less tightly than boron, which has 3 valence electrons, and those 3 valence electrons are free to move throughout and hold them closer together. Those also, using lithium and boron as examples again, lithium is a larger atom. They're in the same period, but it's a larger atom because there's less protons in the nucleus, so the effective nuclear charge is less than that of boron. So boron would be smaller. So 2 reasons that why boron would be held more tightly than lithium would be. So some important properties of metals: they are conductive. We know that. We know that we can send electricity through them, and we know that that conductivity is high, and that's due to those delocalized electrons being free to move and carry a charge. They are also malleable and ductile, which means that I can bend them, shape them, and pull them into fine wires. And this is because the cations can move in groups without breaking those lattice structures, because they're not bonded to each other, and this results in high malleability and ductility. The melting point is going to decrease as bond strength decreases. So the group 2 metals have a higher melting point than group 1 metals. Period 2 metals have a higher melting point than metals in lower periods. So we're doing comparisons here. We're saying that if they're held more tightly together, so if they have more electrons that are being shared from their valence groups in that delocalized sea of electrons, then they're going to be held more tightly together. And if they're held more tightly together, they're going to have a higher melting point. If they're looser, so those low electronegativity values, the group 1 metals, those only have one electron to share, and so they're not going to be held very tightly together, and as a result it's going to be easy to break those electrostatic forces between them. They're going to be able to get enough energy at a lower melting point or at a lower temperature to melt. Metals can form alloys, and what an alloy is a mixture of 2 or more metals. This also includes alloying components made of nonmetals. And some examples include brass, steel, and amalgams, not just dental amalgams, but amalgams in general. And an amalgam contains mercury. We've talked about that briefly. We foreshadowed that in the last unit. Alloys generally have greater strength and resistance to corrosion than their parent metals, so 2 different types of metals together generally is better than 2 different metal or 1 metal on its own. And alloys can also have greater ductility and enhanced magnetic properties depending on which metals we're using.